this is the testing 157, good. Earth to control, yes. This is the part of of my series of talks as I start wandering into areas where I am less sure of what's going on there. So you should feel free to chip in if what I'm saying is wrong. I've also taken the liberty of interpreting context in the broadest sense possible. Therefore, there will be a large slice of history coming into some of these talks. That's partly because before I decided to become an astronomer, I was wanting to become an archaeologist, but they told me that I couldn't be an archaeologist because I needed to learn how to speak Swedish because of the bleeding Vikings. But I've always been interested in history, and I think the context is actually, from that side, is important because what people did in the past and the mistakes they made in the past can definitely inform what we do going forward. So what I'm going to talk about here, this is kinematics. So most of these talks are kind of leading up to one of the things that Michael wanted me to talk about was the field population and specifically the sun, where did the field come from, where did the sun perhaps come from. So there are various things here talking about the general characteristics of the field tracking into that question, or my perspective on that question. So we're going to talk about galactic kinematic models. We're going to go back and talk about Kapteyn's star streams, because they come through in terms of moving groups. Galactic rotation, velocity ellipsoid, just basic stuff there. I'll talk about what we know about local stellar kinematics from relatively modern observations, and talk about velocity evolution, the age-velocity dispersion relation, and then get on to talking about something that I'm reporting what I read in the literature for this. This is about orbit migration, which is the dynamical effect de nouveau, or whatever.
I have a question.
Yep, already? Well done.
Why is there always a dog on your
because I like dogs. It's my signature trademark. And we've gone through lots of dogs, so there's lots of different dogs.
Actually, Neill, the answer is dogs are cool.
That is true. Okay.
Where's the dog here?
This dog is actually an astronomical dog. Her name is Alma. She's large, fuzzy, and warm. Okay, so going back to where a lot of this stuff started, there are two remarkable people who were entirely synergistic in the way that they worked, entirely complementary. This is David Gill. He was born near Aberdeen. His father was a clockmaker. He actually went to Marshall College before it became part of Aberdeen University. He was taught by James Clerk Maxwell before Cambridge. Well, actually what happened was that there were two colleges in Aberdeen, and they merged, and they could only keep one physics person or natural sciences person, and the other guy was the better teacher, so they kept him, and James Clerk Maxwell went to Cambridge, which shows Aberdonian great forward thinking, I have to say. But anyway, Gill went to some classes there. He didn't actually get a degree. He went to work for a local Lord Crawford, who had his own observatory up there at Dunecht, which is near Aberdeen. And Gill was the main astronomer there. He was self-taught. He was an extremely good instrument builder. And eventually, he became extremely well known. Eventually, he was employed down at the Cape of Good Hope as Her Majesty's astronomer at the Cape. That was around about the 1870s, I think he moved down there. Meanwhile, Lord Crawford gave up astronomy, and what he did was he gave his domes to Edinburgh. So those cylindrical domes, if you've been to the Royal Observatory Edinburgh, those cylindrical domes came from Aberdeen. And the telescopes came there too. That's one of the telescopes in there. Actually, I think that's one of the telescopes at the Cape. And Lord Crawford also gave his large collection of literature. There are all of these fantastic medieval books sitting in the library at Edinburgh with the things that you turn around to watch the Ptolemy's epicycles and so on. So a lot of that came from Crawford. Anyway, David Gill is down at the Cape of Good Hope. Jacobus Kapteyn was probably one of the most, he came from a fairly eminent family within Holland. He was appointed to become the director of Groningen Laboratory. And he and Gill encountered each other because Gill, actually, I should say Gill, one of Gill's main contributions to astronomy came in 1882. There was a great comet in 1882, and one amateur photographer at the Cape wanted to take a picture of it. So they strapped the camera to one of the telescopes at the Cape, and they took this picture. And the thing that Gill noticed was that you didn't just get the comet, you got the stars. So he became a strong proponent of astronomical photography. He was one of the main people pushing the Carte du Ciel, which was the big all-sky survey that started in 1875 and finished in about 1960. One of the great examples of international non-cooperation. But, I mean, so, in fact, Gill was so frustrated waiting to start it that I think during some of the meetings for the Carte du Ciel, which were held in Paris, he met Kapteyn. Kapteyn was at an astronomical institution with lots of people working for him, but no telescopes. Gill was Her Majesty's astronomer at the Cape, with people working for him who could take data but could not reduce it. Put the two together, Gill actually paid out of his own pocket for the Cape Durchmusterung survey, which was a southern photographic survey. He shipped the plates to Kapteyn. Kapteyn had his computers, that is, people, sitting there, measure them. They put them together, and that basically came out as the Cape Photographic Durchmusterung. And that was the first real photographic sky catalogue that came out from the collaboration between those two. And then Kapteyn used those data to really reinvigorate galactic structure, to invigorate looking at the general properties of stars, stellar motions, and so on. He also started the Selected Area Project, which was basically a grid of, I guess, every 15 degrees or so in the sky, you were taking photographic plates to probe the galaxy as a whole. So that's the introduction. One other point, Kapteyn, to do the selected area stuff, Kapteyn collaborated with the Carnegie Observatory in Pasadena. He started what I've called the Dutch invasion, because there's all these people that came after him. Adrian van Manen went to Carnegie. Gerard Kuiper went to Chicago, and then he took over. He was largely influential in starting up the observatory in Texas at McDonald. Adrian Blau, who has figured largely in this meeting, visited Chicago in the 1940s for a year or two. Oort just visited all over the place. Dirk Brouwer went to Yale and led the department there for many years. That's Peter van der Kamp. I think it was Allegheny Observatory he was at. He's the Barnard star guy, nearby star person. Swarthmore, okay. Martin Schmidt, climbing slowly into the picture, arrived at Caltech in 1959 and discovered quasars. And then there's Bart Bok, who was in Harvard, who went away to South Africa. There's Willem Leuten, who came in on the East Coast and then pinged across to the West Coast and then ended up in Minnesota. And Bart Bok came back. The other title I have for this is the Dutch exclusion principle. Because apart from Blau, you could never have more than one Dutch astronomer at an institution or they started fighting. But I'm not going to put that on the slides. Okay, anyway. So that's the entertaining, I hope, start before we dive into this. So Kapteyn's investigations were framed in terms of his picture of the galaxy. And I don't know how much you know about this, but you may remember, back in the beginning of the last century, there was still this big debate as to what the galaxy really was, how big it was. One of the big influencing factors, and this is something that there was proceedings of the 100th anniversary of the Groningen laboratory. There was an IU conference there in 1985. There are several historical talks intermingled through that volume. I think it's IU 106. One of the big things that people didn't come to grasps with at that time was interstellar dust and reddening. I think Bob already talked about the Bok globules and how people were wondering if there were holes. There was some talk in even Kapteyn even mentioned that there might be interstellar absorption, but nobody had any conception as to how much of it there really was. And the interstellar absorption is why Kapteyn's galaxy was so small. I mean, basically, he has this is his galaxy. It's going out to 10 kiloparsecs either side, but the scale length is only about it's falling off to 10% of the density from a central sun, 2.5 kiloparsecs out. And the reason why that is because of reddening. If you count stars you don't allow for reddening, you think you've got a small galaxy. It's a flattened system, but it's a small galaxy. Anyway, within that, so the take-home message from that is that there could be something that's really staring you in the face as obvious, that afterwards you'll kick yourself for not doing something about it, because, I mean, this was, I guess Piet van der Kreutz is an interesting article where he thinks that Kapteyn gets a bum deal because he did so much really good work, but there were a few things that he didn't get quite right, and it's the few things he didn't get quite right that people remember. And everybody talks about Shapley, and Shapley measuring the size of the galaxy, forgetting that Shapley's conception of the galaxy was entirely wrong too. So anyway. Okay, so within the system, Kapteyn expected to find basically random stellar motions. He didn't find random stellar motions. He found that there were systematic trends in proper motion in different parts of the sky, typically two systematic trends, his two star streams. And this is a concept that came into astronomy in the early 1900s and really was a big question for a good 20, 30 years after that. So this is a typical kind of, basically if you plot up the proper motions in a given area of sky, you find that there are these two kind of directions, trends among the proper motions in that area of the sky. So part of the answer for that came out. I don't think we need this. Oops, no we did, okay. So, 1915 or so, Karl Schwarzschild came up with a different concept for stellar velocity, the same kind of concept that we use now, the velocity ellipsoid, where you characterize the stellar motions. And again, it's important to think, and I know this came at the back of a James Binney paper as well, that you can characterize the velocities of objects in 3D as an ellipsoid with velocity dispersions in u, v, and w, orthogonal coordinates that are, well, you can, any orthogonal coordinates, I guess I'll talk about u, v, w later. But anyway, so you have three orthogonal coordinates. If the ellipsoid is asymmetric, then when you look in different parts of the sky, you will see these trends in motion, just because if it's a higher velocity dispersion, you're going to see velocities trending in that direction along the long axis of the high velocity dispersion. So that was a kind of an explanation for why you could see star streams, but the concept still crops up in the literature for the next 30, 40 plus years. So it was a long-lived concept, and especially in terms of dispersing star-forming regions. That's the concept that's come through when we talk about moving groups. Ursa Major, I think actually even Bob mentioned the Ursa Major and Taurus groups. So Oort and Lindblad took this a step further. In the 1920s, Lindblad showed that the motions were best explained in terms of a rotating galaxy, with the sun not centered and a rotating system round about there. Oort essentially expanded on that and got the general description of the concept. So it wasn't until the mid-1920s that we were really starting to get to grasp with they were really starting to get. I'm not that old. With what the galaxy we lived in looked like, and starting to be able to be in a position where you can form a kinematic model for what you expect to see. So I think the tag for this historical by-side is that things that large-scale effects within the galaxy can affect small-scale measurements that you're making. So just something to bear in mind. And you need to understand your sample when you're analyzing things. Okay, so this is just talking about UVW. U is positive towards the galactic center. V is positive in the direction of rotation. W is positive towards the North Galactic Pole. And the North Galactic Pole is defined to be at that position in 1950 equinox, which is, what's equinox? Thank you. Well done. And these are just the sets of equations, which you can't read from there, but you can read in the slides afterwards. Okay. So Denon, after Hipparcos, I mean, this ties into Gaia. Hipparcos revolutionized, again, this area of basic astronomy because it gave you it gives you accurate measurements for an order of magnitude, even 2 orders of magnitude more stars than you had before. So there is a series of papers by James Binney, often in collaboration with William Denon, looking at basic concepts in kinematics, local kinematics. And they're all based on a sample of about 18,000 stars that were picked out of the Hipparcos catalogue that have got accurate parallaxes accurate to better than 10%. And the reason they put that cut in is because of the Lutz-Kelko corrections, which bias things horribly as you go to larger errors. All sky coverage, it cuts out the evolved stars and brings it down to 16,000 stars. And then combined it with spectral catalogues to get a kinematically unbiased data set where you have reliable distance measurements. Looking at that distance set, you then come out with these kind of really fundamental measurements. So this is what's known as Parenago's discontinuity. This is B minus V color, and these are W, U, and the total space motion S, and the rotational velocity V for this sample of stars. And what you see is that there isn't really any kind of trend in the, actually no, what's S? S is the total velocity dispersion, I'm talking Havers. So yeah, S is the total velocity dispersion, V is the rotational velocity. So there's no trend in U and V with color. Once you go to V, the rotational velocity, and S, the total velocity dispersion, you see that for early type stars, so O, B, A, and F stars, the velocity dispersion and the rotational lag are low. As you go to cooler stars, there's a trend to higher velocity in both of them. The reason why that is, I think most of you probably know that, as you're going down here, you go down in main sequence lifetime. At this end, you're looking at young stars. An F star has a lifetime of what, around about 300 million years. So down to this end, you're just sampling the most recent stars that formed within the galactic disk. As you go to redder stars, you're getting a larger and larger sample in terms of age. Once you get down to about a G5 star, G6 star, you're getting everything that was born since the beginning of the galactic disk. So what this is telling you is as you get down to older stars, the velocity dispersion and the mean rotational velocity with respect to the local standard of rest lag. In Parenago, it's Parenago's discontinuity because Mr. Parenago found it back in the 1950s. So yeah, it's main sequence lifetimes. And I guess this is just showing the same result, but for two different catalogs. Yeah, a reanalysis in 2009 basically pulls out the same relations. So why does the velocity dispersion increase with age? This is something that we talked a bit about. We actually talked a bit about it in terms of the scale heights of the galactic disk. The concept for why the velocity should increase with age goes back to Lyman Spitzer and Martin Schwarzschild in 1951. So stars are born in clusters with low intrinsic velocity dispersions. They interact gravitationally with other bodies outside the cluster, and they acquire peculiar velocities. I mean, Bob's been talking in terms of relaxation within the cluster. A star is going to encounter other stars outside the cluster, and if it encounters enough of them, that can change the velocity. Now, Spitzer and Schwarzschild made a simple calculation, and they found that star-star interactions were not going to be important on galactic timescales. Essentially, it would take 10 to the 14 years to relax the Milky Way, in the same sense as it takes 10 to the, 6 or 7 years to relax a globular cluster, to relax a cluster. Was that timescale right? Good. I was listening. What you need is a more massive perturber. Now, what Spitzer and Schwarzschild suggested was that giant molecular clouds, or I guess they call, interstellar clouds is what they called them at the time, could play that role. So if you have a 10 to the 5 solar mass object, that can do a lot more in individual whacks than a 1 solar mass star. And in that case, you can actually get down the relaxation time to about 10 to the 9 years, which in 1951 was about the age of the universe, but it's around about less than 10% of the age of the universe. And this is the equation from the paper, the relaxation time, in terms of the mass of the object and the number of objects. So just to read from their paper, the conclusions. At an early state of the galaxy, the interstellar matter had large random velocities, probably corresponding to violent turbulence with great density fluctuations. At this stage, all population 2 stars were formed out of the interstellar matter. Subsequently, the velocities of interstellar matter soon decayed to their present average value. Ever since then, this settling down process, the population 1 stars have been forming out of interstellar clouds at a more or less constant rate. Only after the settling down process was there enough time for interstellar grains to form abundantly. Well, that bit's wrong. Hence, grains did not play a role in the formation of population 2. Grains don't really play a role in the formation of population 1 either, but debris, metallicities does. So this accounts for the different chemical composition. All stars are continually having encounters with massive cloud complexes. The relaxation time for high velocity stars and encounters with those large clouds is too long. Basically, the halo stars spend too little time within the disk of the galaxy to have enough interactions for them to be relaxed. But the disk stars, it's short for low velocity stars, so that star cloud encounters have speeded up the older groups of population 1 stars markedly. And this accounts for the increased velocity dispersion of late dwarfs and red giants as compared with early main sequence stars. So this is actually quite a fundamental paper. And I guess also the question came up yesterday, the day before, why would white dwarfs or brown dwarfs have the same scale height as M dwarfs? Well, the answer is that they're in a system where the most massive objects are 10 to the 5 solar masses. So if you think of a relaxation where you're going from 10 to the 5 solar masses down to 1 and then 0.1, you know, there isn't, in that kind of scattering system, it doesn't seem to me that you would expect any difference between a 1 solar mass object and a 0.1 solar mass object when you have such a high mass. Any kind of mass segregation would be in the high mass object. But I could be wrong there. Anyway, this concept, Bacall took the same idea and looked at wide binaries within the galactic disk and said, can we set limits on the number of black holes in the galactic disk based on the number of wide binaries we see? It's exactly the same concept. And this is his plot of the destruction rate for wide binaries as a function of the mass of the object. And here's the destruction rate comes up to about 20% for objects that are getting into the massive black hole range. So, okay. So Roland Wieland took this concept further with the stellar diffusion calculations, basically calibrating using observations how this velocity dispersion changes with age. What he did was to take nearby star data and basically looked at this set of stars up here. It's essentially from roughly F stars up to OB stars. He looked at the velocity dispersions of those groups as a function of U, V, and W, and that's what's plotted here. So this is the turn-off age of that population, and this is the velocity dispersion. So by looking at a group of B stars that are 100 million years old, and you find they have a velocity dispersion about 5 kilometers per second, you look at a group of F stars that are maybe 200 million years old, you find that they have a velocity dispersion that's maybe 10 kilometers per second. You can start to track out empirically how the velocity dispersion changes with time. And basically what he found was that the velocity dispersion could be described as an increase based on the age to the 1/3 power. And the acceleration tops out at large sigma. And the reason why that is that, and as Bob said, everything's moving. So the faster you move in the W direction, the more time you spend out of the plane, the less time you have for encounters. So you have this asymptotic, actually it looks like a runaway thing there, but it basically, it flattens out around about 10 to the 9 years. Okay. Asymmetric drift, that's the change in the rotational velocity. I think this you can think of in terms of a kind of energy equipartition argument too. There's two main sources of energy for stars in the galaxy. It's either rotational or it's pressure. In the case of the galactic halo, it's all pressure. There's no rotation. In the case of the disk, it's mainly rotational. But if you start to increase the velocity dispersions, you're taking some of the energy out of rotation and putting it into random motions. So what happens is, in the same way as the the velocity dispersion increases with age, the rotational lag of a population will decrease. So you have, as you go to an older age, you start to rotate at a somewhat slower velocity, on average. And that's what this is plotting here. The correlation between the rotational lag and the velocity dispersion. Again, from Danon and Binney. And the sun has a very, well, we have this concept locally of the local standard of rest. That's the velocity that's an exact circular motion around the galactic center. We're moving at about a total motion of about 18 kilometers per second relative to that. Okay, so what do stars look like in terms of their velocity dispersions? So this is nearby stars, M dwarfs, and this is another example just of how the velocity dispersion increases with age. You can segregate M dwarfs into stars without H alpha activity and stars with H alpha activity. H alpha is produced in the chromosphere. It's driven by magnetic activity within the star itself. That magnetic activity declines with time. So if you select stars that show prominent H alpha, they are either young stars, or this is the one caveat, they could also be a close binary system, because those are spun up with age. But if you look at the velocities here, you can see that for the non H alpha systems, the typical velocity dispersions are 40 in U, 30 in V, 25 in W. And the H alpha subset, they're somewhat 27, 23, 21, lower velocity dispersions. That's a sign that these are young, it's confirming that these are younger than the M dwarfs. And now this is getting into the probability plots, which I actually looked this up, and I agree. Quantile plots is indeed what they are. I'd never actually heard that term, but yeah, this is plotting up the, I guess it's the standard, the normal quantile plot for U velocity. So that's taking the M dwarfs, and as I said, plotting up this is U velocity, and then the deviation from the mean of the sample. And you can see it's close to linear in the center here, and then you have the edges, it tails off. And then the central velocity dispersion you find from this is 35 kilometers per second. If you want to fit the outer part, you've got a 52 kilometers per second here. So you could represent this set of stars as a mix of two components, a low velocity dispersion component and a high velocity dispersion component. In V, it's more complex. V, you always have this tail towards going negative means you're rotating more slowly. And you always have a tail towards that direction. The velocity dispersion is more complex. Again, it's not a simple single Gaussian. In W, you can fit it again with two Gaussians, but again, it's not a simple single Gaussian. And putting it all together, so the nearby stars have a velocity dispersion that is somewhat more complex than a single Gaussian. You can represent it by combinations of, by multi-component population, by combinations of Gaussian. But as you should know by now, just fitting two components when you can't fit one is not necessarily a good answer. But there is something interesting going on in that velocity distribution. Okay, and you have, let me skip past this, you find the same thing. So now let's go back to star streams. And another interesting astronomer, Olin Eggen. So in the mid-1930s, Bart Bok had identified what he called moving groups, or star streams, which he attributed to dispersing fragments of star-forming regions. Olin Eggen carried that on. Yeah, he's an avid stellar photometrist and a collector. The collector part, I don't know whether many of you have heard this, but Eggen was at Tololo when he died. He was the staff astronomer there. They searched through they didn't search through, they basically archived his material. In the course of that archiving, they found some letters that George Airy, the Astronomer Royal for Britain, had written regarding the discovery of Uranus back in 1843. That there were some letters that appeared to indicate that maybe the French had found Uranus first, and that Airy was prepared to acknowledge that. How those letters got into Mr. Egan's files, nobody quite knows. He did work at ROE in the 1950s. But there was a little stir. If you look back through the journals, you'll see there was a little stir, I think 5 or 6 years ago, about how those letters could have been hidden to try and preserve British priority. I don't think Egan actually wanted to preserve British priority to anything. He was an American. So he went through his life identifying moving groups. This is a typical Egan diagram of what the Hyades moving group looks like, the Sirius group. Here's a list of some of Egan's moving groups. He had the Praesepe cluster in the Hyades group, the Pleiades group, which included Alpha Persei. There was the Sirius moving group, the Ursa Major moving group, the Zeta Hercules moving group, the Epsilon Indi moving group, which only had 14 stars, the 61 Cygni group, Sigma Puppis, Eta Cephei, Wolf 630, that happens to have Van Biesbroek 8, one of the coolest stars in it. Groombridge 1830, this only has 5 stars, and it's a subdwarf, it's a halo group. And HR 1614, and looking through all that, once the immediate reaction is, well, this doesn't really make a great deal of sense at all, because, as I say here, the Pleiades group, if you look at the individual stars in there, they have ages running from 10 to the 7 years up to 10 to the 8 years. So to think of this as some kind of coeval of a star-forming region dispersing seems strange. However, HR 1614, the interesting thing in there is that he selected those based on their velocity. But when you looked at CM is a metallicity indicator, a combination of some weird DDO photometry, I think, plus something else. They actually have a consistent relation in that as well. So somewhere buried in there, there may be something that's relevant. And in fact, as we'll see, that in fact turns out to be the case. Let me say that people are still doing this. This is a complete irritant to me. There are some people who are going in there looking at M, L, and T ultracool dwarfs, looking at their space velocities and saying, aha, these could line up with the Hyades. The big thing to remember when you're doing that is that if you're saying you've got some star-forming region that is dispersing, and you're saying nearby we're measuring a bunch of these L and T dwarfs, these L and T dwarfs have very short lifetimes. You're sampling a very small part of space. If you try and integrate that over the whole space and the whole lifetimes and go down to the other systems, you're going to end up with a remarkably strange mass function for the parent cluster. Nonetheless, it's still appearing in the literature of people who are wanting to add to these moving groups. So what up? Sorry.
Did you say L and T stars have very short lifetimes?
So it actually it depends on the mass of the object. But the thing to remember for a brown dwarf is that it's always changing in temperature. So what happens is that for most objects lower mass than about 0.05 solar masses, they actually move through the L dwarf spectral type really pretty quickly, less than a billion years, and then they end up in the T's. And I say the short time, obviously they spend a long time down at those temperatures, but to be visible to us, they have to be up at the early types. So, yeah, you're always picking out the most massive brown dwarfs because they are the ones that live the longest, and even they don't live terribly long. Okay, so what is happening? So this is again going to the, and this is velocities again. One of the other, Denon also looked at the Hipparcos data to look at the velocity distribution this is in the V and U, and in W and V, and split up by color. So this is B minus V less than 0, B minus V 0 to 0.4, 0.4 to 0.6, 0.6 rather than 0.6, and then non-main sequence stars, and this is everything together. And the interesting thing is that you don't see this nice Gaussian distribution in there. You actually see clumps, and you see clumps that happen to line up with the proper motions that Egan was saying were different groups. So what's going on here? I mean, there are clear concentrations in the UV diagram that are, it's not a completely random process. There's something putting systematics in there. In particular, this kind of extension down here is what Egan called the Zeta Hercules group. So there is a real signature in there of something going on within velocity space. The Arcturus Group was another group that Egan picked out. Ken Freeman and collaborators down at with the RAVE survey, radial velocity survey, they've looked at the stars that fall in that region in space, and this is a complicated diagram, but the main thing to take out of that is that it's not, when you look at the stars selected by velocity, you don't see what Egan saw for HR 1614. There's a range of metallicities in there, there's a range of ages. So it's not a chemically homogeneous sample. It's not a moving group of stars that form together, but somehow or other there is a concentration in the velocity space. So what's happening? Well, Danon actually, in his paper in 1998, picked out a number of things that could be going on. Scattering by small random perturbations, interactions with large transient perturbers, and forcing by regular non-axisymmetric components of the gravitational potential, like the central bar, a long-living spiral pattern, a triaxial halo, or the Magellanic clouds. And that actually seems to be what's happening. And that's kind of the punchline then. So that then brings us on to migration. And I mentioned this back in the first talk, that there are suggestions that the sun wasn't born where it is now. Those suggestions come from two things. First, the position of the sun relative to in metallicity, specifically oxygen abundance, relative to the oxygen abundance of H2 regions in this region of space. It's more metal rich.
Is it overabundant or underabundant?
It's overabundant. It's overabundant in that plot. It would actually be spot on if you moved it down. But I was just thinking about this. If you believe that metallicity increases with time, then 4.5 billion years ago when the sun formed, if this diagram scales, it was probably overabundant for the oxygen abundance in the galaxy at this location 4.5 billion years ago, regardless of whether you believe the old or the new oxygen abundance, if that was clear. The other diagram relation that led to some suggestion of motion within the galaxy is this diagram here, which is the age metallicity relation for nearby stars. So this is abundance, metallicity, and this is age, 1 to 10 billion years. This is from the figures from Selwood and Binney, but this is actually from data that Edwardson collected and published in 1993. The expectation is that you build up metallicity with time. If that were the case, you would expect to see a fairly clean relation here, in that the oldest stars at this location were also the most metal-poor stars. What you see is a big dispersion. And there's two possible reasons for that. One of them is that your ages are wrong, and you're just mixing things up that way. The other possibility is that you're actually bringing in stars that were born in different parts of the galaxy. So if you imagine you have a nice clean, over the galaxy as a whole, it's metal-rich in the center, it's metal-poor on the outside. Imagine that just scaling with time. If you can mix stars that were the same age but formed in different locations, you could mix up the local velocity, the local age metallicity relation, so you get this broad diagram. Yep.
I can't see from the scales there. What's the scatter in the top block compared to the scatter in the bottom block?
This is about, well, I mean, the formal scatter here is about I would say it's about 0.2 dex. The formal scatter down here is close to double that. But I would say we can actually measure those more accurately than we can measure those. But
You can see what I'm thinking.
Yeah.
If right now there's a spread in oxygen abundance at the center of the circle, then
right,
it doesn't necessarily mean it's coming from somewhere else. It means we're locally in the
right. No, that's certainly true. There must be an intrinsic dispersion that fits in there. But this, like I said, these were the two rationales for probing and saying, should the sun have formed somewhere else? And so just the general scattering process that the Spitzer-Schwarzschild process will lead to stars moving. You can take the velocity dispersion, and you can obviously, as you increase velocity dispersion in U, you're going to move to larger and smaller galactic radii. that can be quantified by this formula here. The excursion in kiloparsecs is the square root of 2 times the velocity dispersion, and you divide it by kappa, where kappa is the epicyclic frequency, which is given by a combination of Oort's constants. But if you have a velocity dispersion of around 43 kilometers per second, you're only talking about excursions of plus or minus 1.6 kiloparsecs. So that's not really going to shift you very much in metallicity. It will add some to the dispersion, but not a great deal. And I guess I should say, well, I'm explaining why people argued for migration. I don't necessarily believe any of this myself. Actually, some of it I do, okay. Yeah, it's insufficient. Right, moving on. So are there other mechanisms? Well, it turns out there are some that have been in this paper by Selwood and Binney was one of the first to point out that you can actually move stars over larger distances using what are essentially resonance effects. I think they're more akin to scattering satellites. So I think they're more akin to the way that we send probes to Mercury than to the kind of normal scattering processes that you think about. But this is an n-body simulation that Jerry Selwood set up, just pure n-body. And over time, a spiral pattern develops in there. And what they found is that within that particles that were close to the co-rotation radius of that spiral could actually be moved outwards. They could gain angular momentum and move outwards, or lose angular momentum and move inwards without changing their ellipticity of orbit. So basically you're just taking something that's on the same, with scattering, you actually increase the ellipticity of the orbit. You're giving it a larger in and out motion. With this, you're taking the orbit as a whole and moving it in one or another direction by changing the angular momentum. And since this has come up, I mean, a number of other groups that have gone into this. I guess this diagram here, this is the final radius. So there's a series of slices here. This is going from 0 to 16 kiloparsecs. The dotted lines in the middle that you probably can't see. So this set of objects here started within a tiny segment there, and they've spread out. This set of objects here, they started at about 5 kiloparsecs, plus or minus maybe 0.2 or 0.3. And they finally, after the full simulation, they end up between 3 kiloparsecs and 12 kiloparsecs. So you're taking objects that were at one location and spreading them throughout the galaxy. And I guess the point is, this isn't just for stars. You could do this for gas as well, cold gas. You can't do it for hot gas. But for cold gas, you can pick something up in this spiral resonance and move it out or move it in. Yep?
And this red is strongest where the spiral arms are?
It's the strongest when you're in the... It actually varies with where you are relative to the rotation period of the spiral arm. So it's strongest at the co-rotation. So where you're... Essentially, co-rotation, you're basically coming... Or I guess there's also the... I have it later on. When you see the same spiral pattern regularly at each orbit, then you get the biggest kick. So I think there, you can see the dispersion is kind of largest round about this radius here. One other thing that they tested in a recent paper was, doesn't matter whether you're in the disk or above the disk. Does the velocity dispersion perpendicular to the disk matter? And the answer is no, it doesn't. You get the same kind of effect regardless of the vertical dispersion. So various other groups have looked at this same issue and come up with essentially the same answer. There's papers by Roskar et al. That have done the same kind of simulations. I think some of them have actually included SPH as well. But it's basically the same thing happens. I guess one thing, the point that this paper makes is that these spiral arm patterns are transient. So they'll form and disappear and form and disappear. So the sweet spot for doing this migration can change with time as spiral patterns come and go. So I mean, it's a very interesting dynamical effect that does seem to be in there.
You can get stuff out to really large radii this way.
I don't. What do you mean?
The galax,
The little things.
yeah.
I don't know. I don't see any reason why you shouldn't. I haven't seen anybody address it, but it might be one way of kicking stuff out there. Yeah, that's a good idea. Nobody's.
They're quite short-lived, I guess.
Yeah.
Producing the...
But I mean, the motion must. I confess I haven't actually found out how quickly this motion happens. Yeah, I see it. But it must be less than a galactic orbit, I think. I mean, presumably it's something that happens relatively fast. That timescale I haven't actually found yet. So the other thing that's going on, of course, is that you've got a galactic bar. This is data from the GLIMPS Spitzer survey. And I guess the main point of this is you can see it's red at the top, and it's not red anywhere else, really. And the red at the top means higher densities of objects, and essentially that's the bar that you're seeing there. And the bar has also been traced out. They've actually got the alignment of the bar is 44 degrees with respect to the Sun galactic center. And there have actually been some observations of red clump giants from 2-mass data that show the same kind of trend there. So you now have this feature in there, another feature within the galactic system that can also start kicking things around. It can behave in exactly the same as a spiral pattern. There's papers by, I believe this, yeah, by Denon in 2000, where he showed that if you're at the inner or outer Lindblad resonance or at co-rotation, you're seeing, there again, you're getting this consistent kick as you're coming around, and that can move gas and stars in and out in the same way as the spiral pattern can. So if you take the local stellar velocities and apply simulations to what's going to happen to them using what we know about the structure within the galaxy, you can basically create things like the Hercules moving group that we see. So these are just plots of, I think it's U against V. There's a whole slew of simulations that basically show that you can take a smooth velocity dispersion and add peaks to it. I mean, this one here is from Bovie et al. It's just a cute diagram of lots of little blips and so on. Basically, the large-scale structure of the galaxy has an effect on the local velocity distribution, and it may well have an effect on where stars are now as compared to where they were before. And obviously, this is somewhere where Gaia can really pay a great deal of benefits. Okay, so that basically was all I was going to cover. Random motions increase with time due to stochastic encounters with massive objects. These objects, so those encounters preserve angular momentum but lead to increased orbital ellipticity. You can also move objects through the galaxy by changing their angular momentum, and that's angular momentum transfer from either spiral arms or with the bar. Yeah, and large scale galactic phenomena can set up orbital resonances. So, couple of questions. Red was a bad color. Can radial migration translate star clusters without disrupting them? I don't know that. It's not clear from the papers. Under those circumstances, is successfully reverse engineering the orbital evolution of any object a realistic prospect? So, thank you.
So how globally should I throw out the idea I had about moving groups when I walked in the door?
I would say almost completely. I don't know that there's any moving group that's been thoroughly confirmed as all the same age and all the same metallicity. I mean,
Hyades and Chrysobeam, for example, the stars associated with that.
I think most of them have nothing to do with Hyades or Chrysobeam. I don't know that anybody's actually done detailed follow-up of the individual stars. I mean, there must be some. Obviously, you're losing stars from both clusters. They must be there some way. But even in 400, Hyades is what, 400 million years?
700.
Okay, most of them are going to drift quite far away. And you remember the 1 kilometer per second, 1 parsec per million years. So I would be surprised if many moving groups actually survive as real entities or real coeval entities.
So you think the clusters don't leave any kinematic signatures?
I think they tend to get swallowed by the field. But actually, that's not true when you're looking in the halo, because you can see tidal, I mean, there are a couple of globular clusters at least where you can see big tidal tails there, but you've got a much more massive system, and you've got much lower background. So I think you're favored in seeing what's going on there. And as I say, there must be some Hyades moving group objects that really are Hyades moving group. But I would suspect it's not as many as you'd like.
What about that bunch of subdwarfs?
They-
They can be kicked out by this mechanism.
I think that was Egan being over-enthusiastic.
Oh, they're not.
Yes, because I got one of his last papers to referee, and he was being over-enthusiastic, and then Alan Sandage told him I was the referee. Egan didn't like me. So,
So actually what I meant by the Hyades and Parenago is something slightly different, which is just that those two clusters, as far as we can tell, are essentially identical.
yes.
Age, composition, everything. So the presumption has always been that they formed together.
Well, are they
Whereby-
really identical? I thought Pricepi was slightly metal poor compared with the Hyades,
I thought it
and
was-
slightly older. But I don't, yeah, I've worked on the Hyades, I've never really worked on Pricepi, so. Mike, can you break the tie?
No. Price seems a little younger too.
Okay.
Actually, Estelle may not.
No,
Okay then.
they're both definitely older than the Pleiades.
Neil, maybe
Yep.
you proved this, but the Ursa Major stream, so that would be younger. It has a better chance to like survive. You know, it's
Right.
not so old that you think it's just totally dead or wiped out.
Yeah, I mean, I don't know. I don't know for certain. So it's certainly possible that it may in fact be a real stream. But I think what you need to do is to get the chemical, measure each star, get its chemical abundance, make sure that they're chemically consistent as well as velocity consistent. Because what we're seeing is that the galaxy can put things together that look as if they're the same, but aren't. So, and on that happy note, dinner time?